Welcome to Engineers Newsletter Live program. I'm Jeannie Harshaw from Trane System and Application Engineering Group, and today we'll be discussing do-it-yourself or easy ways to analyze chiller performance. Analyzing chilled water plants and optimizing their performance with building loads is desirable to minimize energy use. However, chiller plant design often is typically set during the schematic design phase when there are many unknowns. Our program today examines a number of quick analysis tools available that can help system designers determine which chilled water plant design options benefit the building owner and result in efficient system operation. To cover today's topic, Trane Application Engineering Manager Mick Schwedler and Systems Engineer Chris Shea will be joined by Charlie Jellin, a Trane Chiller Marketing Engineer. We'll start with an overview of what criteria is needed to make an accurate analysis. Then we'll walk through some of the various tools and methodologies available today. And finally, we'll discuss a new tool available from Trane and walk through an example chiller analysis and then compare results. So Chris, would you get us started with what makes a good energy model?
A building energy model's purpose is to help owners and designers make sound investment decisions. Although a typical model shouldn't be used to predict absolute energy use, an accurate model can help designers determine the best options to deliver long-term cost and performance benefits based on the purpose of the building. Final purchasing decision should be vetted with proper justification. The same is true for selecting a chiller or chiller plant in the early planning stage. Many of us know that preparation time in the beginning of a project is often compressed. The process of finding the right tool, recognizing the strengths and limitations, as well as engaging the various stakeholders becomes critical. With limited information and budget, many assumptions have to be made early on. There are many existing tools available in the marketplace, so there is no need to spend valuable time reinventing your own tools. Besides providing appropriate accuracy in each stage of design, these tools can often account for your locale and market. Leveraging these tools also makes comparing energy use between various design options much easier. Choosing a tool that is versatile for various design and construction stages will help ensure the outcome reflects the changes of design. Finally, following the charted process consistently facilitates better tracking documentation and open communication for project stakeholders. Here are typical stages of the design. Energy modeling offers the greatest benefit at the early conceptual and schematic phases of design. During the initial phase, the data garnered during the modeling exercise, such as evaluation of site location, orientation, and building mass, can enhance the design with little to no cost. As the project is going through this stage, changes make more expensive and difficult to implement. During the design development phase, designers and consulting engineers often spend the majority of their time refining options and selections through modeling results. Fine-tuning chiller plant specifications and analyzing lifecycle costs also happen in this stage. The final stage of design is construction documentation. Besides serving as the primary source of reference, construction documents are essential files for the owners and local code officials. Within this phase, the energy model can be further refined prior to actual building construction. And once construction is complete, a calibrated energy model can also be generated for measurement and verification after building occupancy. So what makes an accurate energy model? The block diagram for design energy model was extracted from Chapter 19 of ASHRAE Handbook 2013 Fundamentals. The orange block indicate the input variable, and the blue blocks are calculated algorithms. The development of energy model through academia, DOE, ASHRAE, and many leaders has matured over time. Since the 1970s, an energy model has been the best tool for assessing energy consumption for buildings. However, because it can be a tedious input process, it often hinders the willingness to use energy modeling software in the beginning of the design. Many energy modeling software tools have responded with default values which dramatically reduce data entry time. This type of improvement has greatly enhanced the usage of energy modeling software. Now, on the other end of the spectrum is modeling performance for a single chiller. This quick assessment also typically happens in the beginning stage of a project. Two efficiency figures that are often used by practitioners and co-officials are full load energy value and integrated power load energy value, or MyPLV. These tools ignore some pretty critical application details such as building load, profile, local weather numbers, and number of chillers in the system, among others. And because of this, according to ANSI AHRI Standard 550-590 Appendix D, a single metric, such as design efficiency or MyPLV, shouldn't be used to quantify potential energy savings for chiller and system performance. Since the designers are chartered to design a high-performance chiller plant, let's take a closer look at some of these key parameters needed for an accurate model. Agree? In addition to parameters mentioned in the standard, we identify a few more we feel are essential, listed here by the order of importance in terms of modeling result accuracy. We could debate in the order, but I think we can all agree that these key parameters should be considered, even in a simplified version of the modeling software. These parameters should be tailored to your locale, market, and application. I won't get into all of them, but let's elaborate on the first four before jumping into our main topic. The number one key parameter is the weather data. Local weather conditions, latitude, longitude, and elevation affect the loads in the building. Blended weather that assume all locations are the same is not an accurate solution. The result based on these assumptions may lead to an undersized or oversized chilled water plant. Next on our list is building type. Different building type may have specific preference for the type of equipment, lighting, HVAC, and fire safety systems. The usage of facility within the building also can vary greatly. For example, schools can be used as designed during the school semesters but host less operating hours during off-season. Healthcare facilities have specific outdoor air requirements for operating rooms and intensive care units. A typical data center facility needs to operate every second throughout the year with some building redundancy, while office buildings can have minimum chill plant loads during the unoccupied or off-peak hours. So building loads can change significantly depending on the building types. And because chiller plant operation responds to the building loads, it varies greatly by building types as well. Another key parameter is utilization schedule. The most common mistake that we see in modeling is occupancy schedules set to available 100%. This assumes that the space is fully occupied at all times. For a typical office building, this may not account for the travel or holidays. Worse yet, if the schedule is applied in a conference room or space with huge occupancy variations, a huge load may be unnecessarily added into the calculation. The last key parameters I will cover is the utility rates. There are many utility rates for various energy types, so results with combined utility rates can often be misleading. Consumption and demand charges can be very different from one utility company to another. This should be accurately input into the modeling tool in order to reflect annual energy cost comparison for buildings or chiller plant. Renewable energy can also come into play when more and more designs are targeting net zero energy buildings. As we indicated earlier, there are a lot more parameters that should be considered for accuracy. But if we consider everything, we are going back to the full energy modeling software that could hinder the initial modeling progress. So up next, Charlie is going to elaborate on how we can make the modeling process simple and fast without sacrificing too much accuracy. Charlie?
If you want to make an analysis easier, you're likely going to have to sacrifice some accuracy. And for most people, that isn't going to be a big issue because making a model easier and saving time go hand in hand. Here are some of the ways you can make an analysis easier. If you're working inside a modeling program, you'll find data packaged together to speed up your analysis. Examples would be weather files compiled so you don't have to enter data for each hour of the year. Utilization schedules are created for common load uses. Equipment libraries are created for everything from pumps to chillers. System types are packaged together to be applied to building loads. And most programs include wizards that help reduce your input time. There's a lot more out there, but I think you get the idea. As Chris mentioned, in the early design phase, the building itself has many unknowns, but you're still asked to analyze the chiller plant. If you're put in this position, using a full modeling package is not ideal. You need to find tools that help leverage your limited knowledge. Programs that focus on filling in the blanks by using inputs commonly available during early design will give the user a confident starting point. For this type of analysis, we often turn to spreadsheets or dedicated programs created for rapid analysis. If you're using a spreadsheet, you'll find they often concentrate on a single aspect of a building or chiller plant. This reduces both input time and spreadsheet complexity. Some dedicated software programs have the capability to create an entire building load profile with just a handful of inputs. This obviously decreases some of the accuracy, but it eliminates the most time-consuming aspect of a building model, which is inputting the entire building just to get the hourly loads. So that was a handful of ways to make an analysis easier, and by no means all of them. The real trick is knowing what assumptions the tool is making, being comfortable with those assumptions, then applying the right tool for your analysis.
We hear a lot about transparency today, so it makes sense that users of analysis tools want those tools to be transparent. Going old school, I pulled out a dictionary and found some great definitions about what we, as engineers, want in analysis tools we get from others. Here were the definitions. First, we want the tools to be right. Don't mislead us. Do the calculations in a way that is technically correct. Second, make sure that we can see what the assumptions are, how the calculations are done, and where inputs came from. Finally, make sure we can understand it. First, so we know and feel comfortable with it and can defend it, but as importantly, so we can explain it to the client so he or she also feels comfortable. Now, there are a few commonly used tools in the industry today: equivalent full load hours, integrated part load value or IPLV, spreadsheets, and full energy analysis programs. Now, let's take a look at some tools people have used to discuss their ease, their accuracy, and their transparency.
Here's what I found for annual equivalent full load hours. The equivalent full load hours means the number of hours an air conditioner would run at full load to consume the same amount of electric energy it consumes on average over the course of an entire year. This diagram might help to understand the equivalent full load hours. The area of these two shaded blue colors represent annual electric energy that should be the same. The equivalent full load hours could vary by the data source. Here's a list of various sources. The idea for using the equivalent full load hours is to simplify energy saving calculations. For example, Energy Star develops an Excel-based calculator to calculate the annual operating savings using equivalent full load hours. The equivalent full load hours in this case is varied by the states. Minnesota and other states also develop equivalent full load hours that vary by building types. Mick will show an example from ASHRAE handbook later on.
Once the equivalent full load hours are determined, a simple equation, shown in the slide, can be used to compute the average annual energy consumption. This is about as easy as it gets. You figure out your equivalent full load hours, and there you go, energy analysis complete.
Well, the equation is certainly transparent, but as Chris pointed out earlier, using a combined utility rate isn't good. And the big question is, where do you get the equivalent full load hours? We need to find an accurate, transparent, reliable, and current number for our building in our climate. So let's look online. Now, I'll get to that one later. Is there a wiki? Hey, Charlie, I didn't find any apps on this one either. But I remembered that the Trane air conditioning manual, the Blue Book, had equivalent full load hours, so I got mine out. In it, there's a table with a handwritten note stating these are from the 1960s. Add 300 to 500 equivalent full load hours to all the entries in the table. I found it interesting that we had equivalent full load hours for shoe stores and funeral parlors, but not some common building types today. So that didn't make me feel real comfortable. Now, during my internet search, I found a newer article from 1998 that mentioned there's an ASHRAE publication with equivalent full load hours of operation. I found the publication, but there are a few pieces of bad news. It was in the ASHRAE 1985 handbook. So like our Blue Book, it's a bit dated. Now, it had information for 36 cities, but not by building type. For example, for Indianapolis, equivalent full load hours varied from 600 to 1,600 hours with no guidance about which to choose, except residential is lower, commercial is higher. So let's just say that doing a calculation using your handheld calculator and ambiguous data from about 1985 and expecting an answer you'd want to trust doesn't give much confidence.
As Chris mentioned earlier, IPLV stands for Integrated Part Load Value, and that's the tool we're going to look at next. It's a single number that tries to give your chiller a rating for how efficient it is at part load. For a true IPLV value, the chiller needs to be selected for 44 leaving evaporator and 2.4 GPM per ton, as well as 3 GPM per ton on the condenser flow with prescribed entering condenser water temperatures, which we'll get to in a little bit. If your selection has values other than these, for example, you're going to use 42 leaving evaporator instead of 44, the part load value becomes an NPLV number, or non-standard part load value. Taking a look at the equation, you can see IPLV and NPLV consists of 4 bins. The first bin, A, is going to be your chiller's kW per ton with 85 entering condenser at 100% load. This bin is given a 1% weighting. The second bin, B, is your chiller's kW per ton with 75 entering condenser at 75% load, and this bin has a 42% weighting. C is going to be your chiller's kW per ton, 65 entering condenser, 50% load, and this has a 45% weighting. And the last bin, D, is your chiller's kW per ton, 65 entering condenser, 25% load, that has a 12% weighting. All right. As a quick example, I'll fill in the kW per tons for the 4 buckets and compute the IPLV. These kW per ton values can be provided by the chiller manufacturer.
To illustrate the limitations of IPLV tool, I placed the block diagram of IPLV calculation and the building energy simulation side by side. The biggest issue comes in with the blended weather profile and blended loads. For weather, this assumes that throughout the entire United States, the outside temperature at any given moment is the same. The chiller plant can be unloaded in the same way in Miami, Seattle, Minneapolis, New York, and Los Angeles. Similar issues comes into play when considering same loads for all buildings. We know something is obviously wrong here, and we can definitely look for something better. Therefore, to have a better and more accurate energy model, we should incorporate these essential parameters.
As for using IPLV or NPLV in an energy analysis, it's just as simple as equivalent full load hours. You take the same equation used for equivalent full load hours, but you substitute the IPLV value for the full load kW per ton. The thought here is that you use the IPLV instead of full load because your chiller plant is not always at full load.
So, is IPLV a step up from equivalent full load hours? Probably. At least it's weighted, but is the weighting right for your application in your climate? And we have the same issues as EQFH. We have to use a combined utility rate that doesn't account for demand, and what number of hours do we multiply by? Bottom line is it's inaccurate. And you can do better in 2016 than a back-of-the-envelope calculation to purchase a $200,000 chiller.
The next set of tools we'll look at are spreadsheets. And these are used throughout our industry for a wide variety of projects. And their ease of use is really a wild card. They could be incredibly easy or too complex to use and understand. It's really up to the user who created it.
I'm really torn on spreadsheets. I've actually seen several that had a lot of tabs, lots of calculations, have been used for years, and that the engineering firm felt really comfortable with. They are transparent, and as long as there are no problems in the formulas, and the person who wrote and understands the inner workings of the spreadsheet is around, they can be really accurate. Unfortunately, most of the spreadsheets I've seen use bins that combine loads and outdoor air wet bulbs. So they don't account for the number of chillers or the fact that a chiller might be at 60% load on a high wet bulb day or on a dry day. In addition, proper modeling of cooling tower approach temperature and the fact that it drops as the heat rejection decreases but increases as the wet bulb drops makes it tough to put in a spreadsheet. So most spreadsheets I've seen just guess tower approach, and the guess is usually pretty inaccurate. So you need to ask yourself, is the spreadsheet accurate and transparent, or is it just easy? Next, Chris will take us through some thoughts on hourly analysis methods.
Well-known modeling tools, including DOE's Energy Plus software, DO2, Trane Trace, aka Trane Air Conditioning Economics, and Carrier's HAP. For a complete energy software tools directory, you can refer to Building Energy Software Tools website hosted by International Building Performance Simulation Association, IBPSA, USA. The best resource in terms of accurate energy modeling is in Chapter 19 of ASHRAE Handbook 2013 Fundamentals. It provides comprehensive information for various energy estimating and modeling methods. For the modeling of the building and HVAC system design and optimization, it refers to as the forward modeling. 3 components are essential to the mathematical model: input variables, system structure and parameters, and output. In addition to these components, ASHRAE also provides a standard test method for evaluation of building energy analysis computer programs called Standard 140. Therefore, an accurate modeling program should at least incorporate these essential components and go through ASHRAE 140 test cases.
Okay, as far as simplicity goes, Trace isn't simple, but it's not supposed to be. There are parts of Trace that will allow you to do a faster analysis, but as a whole, Trace is on the far end of the simple scale.
Hey, I helped write Trace. Back when we ported it from Cloud 1, we used to call it a mainframe computer, to your desktop. It's robust, accurate, great for use for performance modeling or lead submissions. But it takes a long time, even with the templates and wizards they've made available. I can safely say I haven't put together a Trace file for at least a decade. Now, most analysis programs are fairly transparent since all the calculations are documented. But since they perform so many calculations and iterations, well, it's hard to replicate by hand. So that doesn't mean that third definition of transparent being easily understandable. In addition, when you're making the chilled water system decisions, all you usually know is the location, what the building use might be, and that the glass will change 5 times before you get to the end of the design. Using Trace during the schematic design phase is kind of like shooting a gnat with a howitzer. Now, if we put accuracy and simplicity on the same diagram, we can see that equivalent full load hours in IPLV are not accurate. And while the concept is simple, we still need to figure out what to multiply them by. Spreadsheets can be all over the map. Often the more accurate, the less simple they are to put together and understand. And Trace is accurate, but takes a lot of time and effort. So far, we don't have any great solutions. Those that are more accurate, more simple, and transparent. We want to share a couple tools that can give you the answers you need and are accurate and simple and don't take a lot of time. Charlie, please take us through the first one.
We're going to take a look at a new tool available for free to anyone called MyPLV. The goal of this tool is to provide accurate chiller performance that bridges the gap between a full building simulation and the overly simplistic and often misleading single metric methodologies of IPLV, NPLV, or full load performance. Since MyPLV's goal is to provide an accurate analysis, the following criteria was included from the start: chiller type and manufacturer agnostic, annual building load profile, local weather, number of chillers in the system, condenser water system control strategy, accurate ROI analysis to guide users in best chiller selection, and easy to use if whole building model isn't feasible. So there's the setup. Let's take a look at it. I'm going to move to the monitor and walk through an example, then explain the inputs in more depth after each section. All right, we'll start on the MyPLV Calculator tab. This is where the bulk of your inputs will be entered. The first two tabs, Getting Started and Frequently Asked Questions, will help guide the user through the tool if you hit a roadblock or need some clarification. The example I'll be inputting is a real job that required some significant oversizing. It's a 710-ton office building in Jacksonville, Florida, that is being served by two 500-ton centrifugal chillers, both with AFDs. The first selection you'll see is unit of measure. Since MyPLV includes over 5,000 global locations, we've included both IP and SI units. Next, you'll select your region, country, state, and city. We'll take a closer look at what MyPLV does with your location selection. Having representative weather data is key to overcoming the problem of oversimplified analysis techniques, which assumes the same chiller operating conditions whether you're in Miami or Quebec, which we know is inaccurate. When you select a specific location in MyPLV, the tool maps to a standard weather zone according to the data set contained in ASHRAE Standard 169. The possible weather zones are shown here. Each weather file contains hourly information for every hour of the year. That's 8760 weather. MyPLV uses the selected weather conditions, both ambient wet bulb and dry bulb, as an input to establish the operating conditions for the cooling tower or the air-cooled condenser. Then based on this information, the program calculates the entering condenser condition for each point of the load profile. Obviously, tower control will have an effect on this value, and we'll look at that in a little bit. But let's get back to our example. The next inputs will be building type, peak building load, and this is total building load, number of chillers serving the building, chiller type, and finally size of each chiller serving the building. Note that MyPLV will always assume that the chillers are equal sized and in a parallel configuration. The last two cells in orange are calculated values, showing your total chiller capacity and plant oversizing. Let's take a closer look at the building load profile selection. For our example, we selected an office without airside economizer. Here's a list of all the possible load profiles, both with and without economizers. You can also see the corresponding hours of operation and days of the week. The load profiles are a result of various ASHRAE standards efforts, along with Pacific Northwest National Labs. They've created a library of annualized load profiles for various building types in all weather zones. The MyPLV tool incorporates 200 of these load profiles within its database. By selecting both location and building type, MyPLV generates one of these 200 load profiles. On top of that, when the user enters a peak tonnage for the building, the program scales the PNNL load profile to the peak cooling tons entered. The result of all this is a building-specific, location-specific, and peak ton-specific load profile that you can now use in a chiller energy analysis. Also included in the MyPLV tool is a custom load profile creator. This can be used if your building type does not fall into one of the standard categories, something like a process load or a data center load. But let's get back into the program and take a look at how cooling tower control will impact your analysis. The tower control can be found at the bottom of the screen. The user will need to enter both full load design approach and outdoor ambient design wet bulb. For our example, we'll use 78 degree for the design wet bulb and a 7 degree approach. This corresponds to an 85 degree design entering condenser temperature for the chiller. The tower control we'll select is fixed temp with a set point of 55 degrees. Let's take a closer look at the tower control. If you're doing a water-cooled analysis, the tower control will determine the hourly entering condenser temperature for the chiller. There are 4 choices for tower control. The first is called full tower fan flow. This control will determine an entering condenser temperature that results from the tower running with full fan speed. You can think of this control as the coldest possible water leaving the tower. The only thing that will limit this control is if the calculated water leaving the tower is lower than the user-specified minimum. If this happens, MyPLV will use the user minimum as the entering condenser temperature for that hour. The tower performance, both approach and design wet bulb, are user input. On the graph, the tower design is donated by the red square. For our example, again, the design tower performance is 7-degree approach at a design wet bulb of 78 degrees. You can see the tower approach linearly degrades to 0 at no heat rejection and also varies with outdoor wet bulb temperatures. As an example, if you're operating a single chiller at 80% load and the outdoor wet bulb is 50 degrees, your tower approach is 12 degrees. This would give you an entering condenser temperature equal to 62 degrees, 50 plus 12, for that hour. The next tower control is fixed temperature. This control allows the user to specify the tower leaving temperature for all hours of operation. MyPLV will use this value unless the tower capacity at the specific conditions encountered cannot achieve the set point temperature. If this happens, the leaving cooling tower temperature will be the value at full fan flow conditions. Here's an example. The user enters a fixed tower leaving temperature of 70 degrees. Using the same graph from the last screen, we'll calculate the entering condenser water temperature for 3 different hours of the day. We'll look at 75, 50, and 25% loads with wet bulbs of 60, 70, and 80 respectively. The calculated approaches for each hour are 9, 4.5, and 1.5. The calculated entering condenser water temperature is equal to the wet bulb plus the approach. For hour 1, the tower could generate 69-degree water, but the user entered a set point of 70, so MyPLV will use 70 for that hour. Both hours 2 and 3 have calculated entering condenser water temperatures above the set point, which means the tower cannot generate the 70-degree set point. In this case, MyPLV will use the calculated values, 74.5 and 81.5. All right, fixed tower approach is the next control. This control will compute an entering condenser water temperature equal to the outdoor wet bulb temp plus the tower approach entered by the user. Again, if this value cannot be achieved, the tower leaving temperature will be calculated by full tower fan flow. We'll do a similar example to the last. We'll assume the user entered a fixed approach equal to 7 degrees. Anything below the approach line will be reset to 7 degrees. Anything above the approach line will use the calculated approach. Again, we'll look at 3 hours, 3 different loads, and 3 different wet bulbs. The calculated approaches are 15, 9, and 5. Only hour 3 falls below the 7-degree fixed approach set point, which means hour 3 will be the only hour set to a 7-degree approach. Hours 1 and 2 will use their calculated approaches because the tower cannot achieve a 7-degree approach at these conditions. The last column shows the entering condenser water temperature for each hour. All right. The last control is chiller tower optimization. With this control, we're dynamically changing the entering condenser temperature to minimize the combined power between the chiller and the tower. All right, so that was a lot of information on tower control. In the future, if you need a reminder on how any of these controls worked, click on the FAQ tab in the lower left corner, and you'll find a detailed explanation of each control. Also note, if you choose an air-cooled condenser, this section will be completely hidden. We simply use the hourly ambient dry bulb as the input for the chiller condenser. Back in the MyPLV tool, we now have the pieces in place to calculate your chiller's MyPLV. Simply click the Calculate MyPLV conditions. You'll see the table populates with a couple different sets of data. First, you'll notice the 4 bins on the left. These are load buckets denoted by 25, 50, 75, and 94% loads. I'll get to why we use 94% in a moment. The next column shows you the chiller tonnages corresponding to the load bins. The ton hours column sums up every hour of operation that fell in that respective bucket. The weighting is that bucket's percent of total ton hours, and the entering condenser water temperature is the weighted average seen for that bucket. The final column is chiller kW per ton, and this needs to be entered by the user. You'll need help from the chiller manufacturer in order to complete this section. Using the percent load and the entering condenser water temperature, the chiller manufacturer can supply the chiller kW per ton for each bucket. Here's an example using Trane's chiller selection program called TOPS. Once all 4 values have been entered, a MyPLV can be calculated. This is the same calculation we showed you earlier for IPLV, only we use the weightings calculated by your inputs. We do not use the design condition to calculate the MyPLV value. We'll show you where that is incorporated on the next tab. The annualized kWh for each chiller is calculated by summing each bucket's ton hours multiplied by the corresponding kW per ton. The next part of the MyPLV tool we'll look at is the bid form. The bid form allows the user to do a quick and simple energy economic comparison between chiller performance alternatives. The first inputs required will be your basic utility rates, $1 per kWh, $1 per kW, and a ratchet rate if you have one. You can see the base column was brought in from the first tab. This is assumed to be the lowest cost option. The only open input is the total cost of the chillers. You can either enter the actual cost or use a 0 and input the difference between the options on the next columns. Below in orange, we see the output for the base selection. The first two, MyPLV and annualized kWh, we've already talked about. Annual consumption is calculated using the annual kWh and the input for $1 per kWh. And the annual demand charge is calculated by first establishing the highest tonnage for any given hour within each month. MyPLV shows you the peak for each month in the upper right table. The peaks for each month are summed together and multiplied by the design kW per ton and the demand rate for the plant. Note that we assume the peak for each month is when the chiller is at full load. To do a chiller comparison, you simply start inputting chiller performance in the next columns. As an example, we'll add a high efficiency option to the bid form and see what kind of payback we can expect. The high efficiency chillers cost $55,000 more than the base chillers. We'll input this in the cost cell. Using the annual consumption and demand fields, we can get an annual dollar savings, which will be used to calculate a simple payback. For our example here, the high efficiency chillers will pay back in 4.3 years. The last feature of MyPLV we'll look at is the Charts tab. These give you a graphical representation of the building and the chiller you've modeled. The first graph we'll look at is chiller load versus entering condenser temperature. The blue triangles represent 1 hour of one chiller operation, and the red squares represent 1 hour of two chiller operation. The vertical dashed lines separate the 4 load bins. The red circles show you the static IPLV points, while the blue circles show you the calculated MyPLV points. You can easily see the 50% load bin has the largest deviation between IPLV and MyPLV. Remember, this bin is given a 42% weighting in the IPLV calculation. This graph also shows you why we use 94% as the highest load bin. This bin consists of loads between 100% and 87.5%. 94% is simply the midpoint. The second graph we'll look at shows plant load versus entering condenser water temperature. This graph does a good job of showing you the cutoff between 1 and 2 chiller operation. MyPLV allows the first chiller, shown here in blue, to load up to 100%, and for this example, that's 500 tons. Obviously, above 500 tons, we switch to 2 chiller operation, and that's shown in red. As expected, 2 chiller operation corresponds to higher entering condenser temps, which is caused by high ambient wet bulbs during the summer months. Looking at this graph, you can see our example plant is primarily handled by 1 chiller operation. If we zoom out, MyPLV shows the overall chiller operation by ton hour, and 86% of the time, 1 chiller can handle the entire plant load. We've probably oversized the chillers in this plant, but there were various reasons the customer wanted chillers this size. I'll be back in a bit to do a comparison using the MyPLV output.
I need to disclose that I fought against a tool like MyPLV for a long time. We have chilled water system analysis programs. Let's just use them. But since people kept asking for something quicker, the chiller group went ahead anyway, and they got a lot of stuff right. Loads. Rather than make guesses, they used the load profiles developed by Pacific Northwest National Laboratories for the ASHRAE 90.1 committee. You can't get much more third party than that. It accounts for building type, location, and use or non-use of economizers. They allow both demand and consumption charges to be included. The profile changes with the number of chillers, as do the weightings, and the number of ton hours is calculated. It also allows different tower control methods. Very importantly to you, it isn't tilted toward Trane, since you get data from each manufacturer at the calculated load and condenser water temperatures. All in all, it's a really well done chiller comparison tool. But the downside is that it doesn't account for chilled water pumps, condenser water pumps, or cooling tower fans. So if you're looking at different system design parameters, configurations, temperatures, and flow rates, we still need a system tool. Enter Chiller Plant Analyzer. Now, Chiller Plant Analyzer is a subset of Trace, but eliminates most of the time-consuming aspects. Let's take a look. The first thing we do is select our base system. We'll use the same project as Charlie. In this case, it's 2 chillers in a variable primary flow system. The chillers are in parallel, and the cooling tower fans have variable speed drives. Next, we select Jacksonville, Florida as our location. By the way, there are worldwide locations available too. Charlie had an office building with no economizer at a design capacity of 710 tons. Now, we could also model the heating plant, for example, if the building is a hotel or hospital and we wanted to consider condenser water heat recovery to preheat the domestic hot water. But in this case, it doesn't matter. When we select Finish, the load profile is made. Development of the load profile is less transparent than MyPLV since calculations are done, but the result is just as transparent since the load profiles can be viewed. In addition, if you want, you can input your own load profiles. With that said, the most time-consuming portion of Trace is the architectural input, and we did all that literally in a minute. Now, all the chiller plant and economic capabilities of Trace are available to us. The next step is defining the utility rates, including demand and consumption charges. Now, this is a really important step. Remember from previous E&Ls that 2 same price chillers, 1 constant speed and 1 variable speed, can differ in design kW by more than 15%, and that's what sets the demand charge, even if it only occurs for 15 minutes in the year. So we define the chilled water plant. In this case, we input 2 chillers with variable speed drives. Each is oversized at 500 tons and is high efficiency. For this, you can either select a library member or you can get input from the manufacturer and enter it. Entering the specific chiller takes a little longer. Next, there's a high-efficiency constant-speed condenser water pump with 75 feet of head and variable speed drives on the cooling towers. You'll note that the dedicated chilled water pump's kW is set to 0 since the manifolded variable primary flow pump is in the system section. Once the base system is set, we can define our alternatives. The first is going to be chiller tower optimization. Instead of driving the tower water as cold as possible, the tower temperature is optimized depending on heat rejection and the outdoor air wet bulb temperature. Now, this was summarized in our last E&L. Chiller kW rises as the tower temperature rises, but the tower fan power goes down with the cube of its speed. We want to find that optimal set point at each operating condition during the year. Within Chiller Plant Analyzer, all that's necessary is to copy the base alternative, then select the same cooling towers with chiller tower optimization control. Now, we considered putting the chiller evaporators in series, but since the customer oversized them significantly in this job, the second chiller doesn't run very often, so it probably doesn't fit for the application. So our last alternative for this building is to use the ASHRAE Green Guide recommendations and reduce the condenser water flow rate. This reduces the condenser water pump size and the cooling tower fan power. The fan power goes down because the inlet water temperature to the tower is higher, making the tower a more effective heat exchanger. This alternative takes a little more input because the chiller, condenser water pump, and cooling tower fan performance all change. So you need to get that information, but I think you'll find it worthwhile when you see the results. A system with lower installed cost and lower operating cost. So, how long did this take to get the results for Jacksonville? 30 minutes, including some interruptions. Then to model Washington, D.C. and Grand Rapids took less than 5 minutes each, because all that needed to be changed was the location and changing the building type to an office with an economizer for Grand Rapids. The final destination, Calgary, Alberta, took a little longer to get the data and put into the program. That's because Alberta has a lower wet bulb temperature. So we created a cooling tower to deliver 80 rather than 85 degrees. Now, we don't want to overpromise the ease of doing it yourself. But the more complex the input, such as tough utility rates, the longer it takes to get and input the information. But the bottom line is that all this was done in a total of an hour, including all 4 locations. Let's ask Charlie to make some comparisons using MyPLV, then I'll come back and discuss some chiller plant analyzer results.
The first comparison we'll make is between MyPLV and NPLV. We'll use the example I just went through in MyPLV. It's a 710-ton office building that uses 2 500-ton centrifugal chillers, both with AFDs. The tower control will be fixed 55-degree set point, which means we'll work the tower as hard as possible to try to maintain a 55-degree leaving tower temperature. We'll compare the results between 4 cities scattered around North America. We'll sort the data in the 4 MyPLV bins, 25, 50, 75, and 94% loads. We'll also compare total ton hours calculated by the MyPLV tool. Inside each bin, MyPLV calculates a weighting based on ton hours and an average entering condenser temperature for that bin. For this job in Jacksonville, MyPLV is showing that you'll operate in the 94% load bin 12.3% of the year with an average entering condenser water temperature of 82.3 degrees. Moving from left to right, that's Jacksonville over to Calgary, you can see some trends starting to emerge. Since this is the same office building and the same chillers in each location, you'd expect the bins to change with location, and they do. From Jacksonville to Calgary, we're moving north on a map. And as the climate becomes colder, so too does the maximum entering condenser temperature. Also, the total ton hours decrease as the climate gets colder, which makes a lot of sense. Now, let's compare MyPLV to the actual NPLV numbers. The MyPLV for this chiller in Jacksonville is a 457. The same chiller in Washington, D.C. is a 418. It's a 410 in Grand Rapids and a 357 in Calgary. The MyPLV is changing based on load, climate, and tower control. The NPLV for this chiller is a 346 regardless of where the chiller will be operating, the load it will actually see, or the tower control you're planning to implement. It is a static value for each chiller. Now, if this job was installed in Calgary, you'll probably be all right using NPLV. You can see the numbers are pretty close. But this job is going to Jacksonville, and the 2 numbers here are not even close. It was this comparison that opened the owners and the engineers' eyes on how they specified chillers for this job.
Next, let's look at the chiller plant analyzer results. In each location, chiller tower optimization saved over 10% of the chiller plus tower energy use compared with driving the tower water temperature down. Then, going to a higher delta T condenser water system saves even more energy and costs less to install. Now, taking a solution to the owner that saves installed and operating costs is about the best you can do. And you can do that in about half an hour. If we base the decision solely on chiller energy use in any of the locations, we would select the poorest performing alternative. Now, this seems counterintuitive because we've heard 2 mantras over the years. The first, the chiller is the largest motor in your system. Do anything you can to reduce its energy use. The chiller is the most efficient part of the system. Coefficient of performance is the amount of useful work divided by the power input. The COP of a good chiller is between 6 and 7. The efficiency of a pump may be 70%, which equates to a COP of 0.7. So intuitively, we know that we should work the most efficient portion of the system, the chiller, a little harder. The second mantra is that the cooling tower power is so small compared to the chiller that it doesn't seem to make sense to reduce tower fan speed in kW. At design conditions, that's usually true. But what happens as load and the temperature the tower can produce goes down? The tower becomes a larger percentage of the system energy use. Let's examine that. At 100% chiller load, the tower is about 10% of the chiller plus tower power. At 25% chiller load, the tower is about 40% of the chiller plus tower power. Especially at lower load conditions, it makes a lot of sense to optimize the system energy by backing off on the tower fan speed and letting the chiller work a little harder. The bottom line is that it's always important to look at the system, and Chiller Plant Analyzer allows you to do that.
Some of you are probably wondering what effect the oversizing from the first example had on MyPLV. For you, here is a different comparison for a 400-ton school with two 200-ton air-cooled chillers, no oversizing. We shuffle the locations around and we'll show you the results of Las Vegas, Seattle, Kansas City, and Houston. For this analysis, we're only going to compare the actual MyPLV number versus the NPLV. Again, you can see the NPLV is static as you move the same chiller from location to location, while the MyPLV value is adjusting based on your building, your location, and your plant operation. Also notice the deviation between the two numbers. Seattle has the best deviation at 4%, while Las Vegas is 14% away. If these values were used in an energy analysis, you can see how you'd get two vastly different outcomes.
For the high school, we used Chiller Plant Analyzer to examine two different system alternatives. With air-cooled chillers, input was simpler and took 40 minutes total for all 4 locations. The first alternative was to change from primary-secondary to variable primary flow. This reduces the pump energy a little, but a bigger factor is that this system's installed cost is reduced since we got rid of the bank of primary pumps. The second alternative is variable primary flow and putting the chillers in series. Even with the higher pump energy due to evaporator pressure drop, putting the chillers in series saved about 3.5% compared to the base alternative. Just as important is that series chillers in a VPF system are much simpler to sequence. So the installed cost is lower due to VPF design, series saves energy, and it's simpler. Now, that's a great trifecta. In addition to the options we walked through, Chiller Plant Analyzer, we could compare heat recovery, thermal storage, water side economizing, and more complex utility rates, as well as other options. Now, rather than looking at another CPA example, let's have Charlie take us through one more using MyPLV.
The final comparison I'll make will concentrate on the effect of tower control and climate on MyPLV. The example here will look at a 2,000-ton peak load hospital with 3 700-ton centrifugal chillers, all 3 with drives. The first graph we'll look at has the tower control set to fix 55 tower leaving. This means we're always trying to maintain the tower leaving to 55 degrees. If we can't achieve the 55, we'll run the tower all out and use the corresponding leaving temp. Each city is showing the percent of run hours in the 3 temperature buckets shown. To explain this a little better, let's take a look at Philadelphia. MyPLV calculates this chiller, operating in a 3-chiller plant hospital with fixed 55 tower control, will have 11% of the run hours in the 65 degree or less bucket. The 75 to 66 degree bucket is the largest with 61% of the run hours. The 85 to 76 degree bucket has 28% of the run hours. Looking at the other locations, you can see how the local climate affects the buckets. Miami has the least amount of run hours in the 65 degree bucket, which makes a lot of sense, it's Miami. At the bottom, we show you the NPLV assumptions for condenser entering temperatures. 57% of the time, NPLV assumes your tower makes 65 degree water or less. 42% of the time, you're operating with 75 to 66 degree water, and only 1% of the time do you have 85 to 76 degree condenser entering temperatures. The second graph we'll look at has similar data, but we switch the tower control to chiller tower optimization. With this control, we minimize the total combined power consumption between the chiller and the towers. When we optimize the tower control, you can see that the majority of all hours fall in the entering condenser water temperature bucket of 85 to 76 degrees. The fewest hours are logged in the 65 degree or less bucket. Now, this might seem like a bad thing. Intuitively, we know as entering condenser temps go up, so too does the chiller kW. But remember what Mick just showed us. Higher entering temps can help reduce total system energy. Again, at the bottom, we show you the MyPLV assumptions for entering condenser water temperature. And again, the MyPLV assumptions are nowhere near the predicted values for any of these locations. You'll also notice the MyPLV assumptions are the same regardless of your tower control. Where MyPLV is adjusting the weightings based on your load, location, and tower control, MyPLV is static regardless of your operation or location. If you think back to the previous E&L, you'll remember we call VFDs on centrifugal chillers part lift machines, meaning you can't slow the speed of the motor until you have reduced entering condenser temperatures. If you use MyPLV for the basis of your analysis, you will always buy a drive on your chiller. The reason being, MyPLV assumes you have 75 degree water or less entering your condenser 99% of the year. You always have reduced entering temps. Don't get me wrong, we like to sell drives on every chiller. Every manufacturer does. But we would love to sell drives that actually pay back in a handful of years. And in order to do that, you need to use a tool that can properly analyze your chiller configuration.
Let's review where we've been today. As professional engineers, your goal is to provide the client with accurate information, understand how that information was developed, and still make profits. MyPLV gives you a simple tool based on third-party load profiles and addresses almost all the shortcomings of using back-of-the-envelope calculations. It lets you compare chiller performance from any number of manufacturers you choose, so it's chiller agnostic. Another piece of good news is that it's really fast. Chiller Plant Analyzer takes a bit more time, but branches out to the entire chilled water plant. Now, we only looked at 2 alternatives today, but other alternatives like series chillers, heat recovery, water site economizing, and other system configurations could also be studied. Both MyPLV and Chiller Plant Analyzer are simple, accurate, and transparent. So you can choose whether you're interested in the chiller or the system. Then, using the correct tool for the job, you can do it yourself and bring more value to your clients in a short amount of time. Jeannie?
Thanks, Mick. As always, we have a number of resources available that provide more information on chiller and chiller plant design and control, including an engineer's newsletter published last December that takes a deep dive into the MyPLV methodology. Both MyPLV and a trial of Chiller Plant Analyzer are available to download at no cost. The bibliography included in your handout provides more information on where to find all of these resources, including past E&Ls. Many past E&Ls are available as continuing education programs on demand and free of charge. So visit trane.com/continuing education for a complete list to satisfy credentialing requirements. And don't forget to fill out a survey and let us know how we're doing. And finally, please ask your local host about details for the remaining Engineers Newsletter Live programs for this year. In spring, we'll be discussing ways to get the expected performance from air site economizers. And then we'll return in fall to discuss new fan technologies and efficiency regulations. And we'll host a program on acoustics in outdoor applications. So please plan to join us. Thanks for your time today. We look forward to seeing you next time.